Okay, so in this video, we're going to follow up with the key ideas that we learned in the first video and apply it to a new problem. So this is the second problem in your notes that we're going to go through. Alright, so in this case we have two ropes and they're both attached to this ninja guy, and it tells us that the mass of the ninja is 50 kilograms. And so we know that we have two ropes that are T1 and T2, and one of the ropes is attached at a 90-degree angle to the wall, and the other rope is attached at a 30-degree angle to the ceiling. Okay, so some key ideas from the previous video that I think you should remember is that number one, the object is a point mass that is in translational equilibrium, and number two, that the vertical components of the tension in the ropes are what is supporting the weight of the object. Okay, so let's launch right into this. I'm going to start by finding tension in rope 2, but before we start any force problem, we need to start with a free body diagram. Okay, so when I draw my free body diagram, I take my object, which is a point, and I draw the forces acting on that point. So I have a tension 1 that points straight out and attaches to the wall, and then I have a second tension, tension 2, that acts at a 30-degree angle below the horizontal. I also have the weight of the ninja pulling straight down right there. And so first off, I do know the weight of the ninja because I know the mass of the ninja. Remember, weight is mass times the acceleration of gravity. So if the mass of the ninja is 50 kilograms and the acceleration of gravity is negative 9.8 meters per second squared, I get negative 490 newtons of weight acting on the ninja. And so remember that only the vertical component of the vectors support the weight. And so I know in this case that the forces in the y direction, because this is in translational equilibrium, are equal to the weight plus the y component of the tensions. So let's see what y components of tension we have here. So T1 is pointing in the x direction, it's not pointing in the y direction, so it has no y component. So I can just completely ignore T1 in this case. T2 is pointing in both the x and the y direction, and so I can draw T2y, and I can draw T2x. Okay? And so I know that T2y is my vertical component of my tension 2, and that plus the weight is equal to the force, the net force in the y direction. And we know that because the point is in translational equilibrium, as before, that the net components add together to 0. Okay, and so my weight, we already solved for that, is negative 490 newtons. My tension T2y, if we look up here, I see that I have a 30-degree angle, and so I can do opposite over hypotenuse and solve for this, and I can see that T2 sine 30 should give me T2y. So T2y is equal to T2 sine 30. Alright? And so I'm trying to solve for T2 in this case, so I'll do some rearranging. So negative 490 newtons divided by sine of 30 gives me a tension T2 of 980 newtons. Okay, so I know that the tension T2 is equal to 980 newtons. And so that's one rope, but we need to solve for the other rope too. Okay, so we know that the forces acting on this point are in equilibrium, and we know that the force in the x direction as well as the force in the y direction must be in equilibrium. And so I know that because T1 points in the x direction, that the component of T2 that points in the x direction must be equal in magnitude to the force of T1. So what does that look like? So basically, I have a force T1 pulling this way, and then on the same point I have sorry, not Ty, it's x, T2x. Okay, so the x component of T2 pulls to the right the entire tension of T1 because it does not pull in the y direction, pulls to the left. And so if we solve this, so we know that T2 is equal to, from our previous work, we know that T2 is equal to 980 newtons. And so I know that the force in the x direction is equal to T1 plus T2x. And I know, if I look at my free body diagram, that T2x is going to be equal to the cosine of 30 degrees times T2. Okay, so I do a little substitution. Fx is equal to T1 plus T2 cosine 30 degrees. Okay, and if you remember from our previous work, all these things are in translational equilibrium, and when things are in translational equilibrium, all the forces add to 0, and so Fx is equal to 0. Okay, I'm trying to solve for T1 so I can get it alone. So T1 is equal to T2 cosine 30 degrees. I know T2 in this case is 980 newtons times the cosine of 30, and I find that T1 is equal to 849 newtons. All right, and that's all there is to it.